Welcome everybody to the session on scaling machine learning. My name is Shri, and we will have 4 speakers for this session. Our first speaker for the session is Kyungtae Kim, and Kyungtae is a PhD student in the Department of Computer Science at Purdue. His research interests include software and system security, and he's going to be talking on VASLs, efficient and scalable deep learning prediction on trusted processors. So before I hand over to Kyungtae, just a minor request. I know you can ask questions on both Vovo and Zoom. However, we prefer that you ask it in Vovo if possible, because we can process the questions possibly along with the answers. So both are possible, but Vovo is preferred. All right, so Kyungtae, all yours. Let me start sharing.
Yeah, can you guys see my, hello? Can you guys see my screen? And yeah.
Yeah, just give me 1 second. I'm going to start sharing.
Sure.
All right, are you able to see the screen?
Yes.
Okay, all yours.
Well, okay. Thank you for the introduction. Hello, everyone. My name is Kyungtae Kim. And let me summarize our work first. So the focus of our work is deep learning prediction running in a trusted execution environment like XGX. So deep learning basically deals with a lot of security sensitive data that is not supposed to be exposed. So to achieve such a goal, SGX is useful because it provides, secure container that is called enclave. So other application and some high privilege software like hypervisor or other operating system cannot access private data inside enclave. But the thing is, physical secure memory is called EPC in SGX. Its size is very small. So if application requires much more memory than EPC size, then page swap happens. Such a page swapping is so expensive, so they can incur like significant runtime overhead. If you think about the deep learning prediction in general, it's too memory intensive. So it requires a large amount of memory resource in order to perform their own matrix computation. So for these reasons, with the SGX protections, the performance of deep learning prediction could be worse because of much more intensive use of EPC. So what we're actually going to do is we first figure out the memory footage, memory usage pattern of existing deep learning predictions. So we first observed some limitations there. That is bulk memory allocation and low memory reusability. So what we actually observed is all the memory buffers used in during layer by layer executions are allocated at the beginning of the execution and deallocated at the end of the execution. So even though each memory buffer is only used in a particular layers, and they occupy their memory resource through the end of the executions. So such insufficient memory management. So can you move on to the next slide, please? Yeah, thank you. So based on this insight, we developed a new deep learning prediction framework vessel that is efficient and scalable, even under SGX protection. So we first keep track of all the memory dependency across all the memory layers, and figure out what buffer is actually used in what layers. So using this information, using this dependency information, we place an optimized memory pool in EPC, where all the memory buffer can allocate from them. And by doing so, we can reduce unused, unnecessary memory space and increase the memory reusability. So other than this, to be scalable even in the multiple enclave prediction, we also design a prediction scheduler that is aware of EPC usage. So we actually only allows a new enclave to launch if EPC usage is within a threshold. So by doing that, so we can prevent EPC thrashing caused by careless use of multiple enclaves. So in our evaluation using 9 deep learning models, we reduced up to 90% of memory footage compared to baseline deep learning prediction with SGX, and more than 50% of latency improvement on average in a single prediction, in single enclave prediction. In multiple enclave prediction, we observed more than the 150% of throughput improvement. So that's it. Thank you.
Thank you. Yeah, thank you, King. Thank you, King Tae. So that's very interesting. So while just a reminder that questions are very welcome, and you have the option of asking this on VOVA and asking questions on Zoom. We prefer that you ask on VOVA because we can persist your questions. So while people are typing the questions, I had a quick question, King Tae. So can you get into the details of how that memory optimization occurs in the secure enclave? So what is sort of, at least at a high level, the algorithm that decides the part of the model that is fetched and brought into the enclave?
Oh, well, yeah, like I summarized, we first, our approach is, our first approach is like a performance systematic study, and using that study, we provide the existing framework, and we observe the, low memory reusability. That is, all our buffers are allocated at the beginning of the execution, and they're located at the end of the execution. So such a inefficient memory management, right? So if you think about the SGS, it's very memory sensitive because its EPC memory is very small. If application requires much more memory than EPC, then page swap happens, and page swap incurs significant memory performance overhead. So in order to optimize this, we just analyze the layer by layer execution. So actually, we keep track of the lifespan of each memory buffer. So that is an important point. Using that information, we can optimize the memory pool and place them in the EPC size, and all the memory buffer will be allocated in the EPC memory in the memory pool. So that is a basic concept of our optimized memory pool. So other than this memory scheduling, we should consider like if we deploy our, in the production environment, we can deploy our technique into like a, just a cloud system, and then we should think about the multiple enclave execution, right? If we can just receive too many prediction requests at the same time, we should take care of them very efficiently and effectively. To do so, we should schedule like enclave creation and distro and termination, things like that. That's the basic idea of our approach. Did that answer your question, right?
Yeah, that's interesting. So I'm not seeing any other questions. However, I myself have a follow-up question. So you mentioned production environments. Do you actually have this running in some production environment, or the production users for this for SGX for optimization?
Well, we actually try to do that. Actually, nowadays SGX is available in the cloud. So if I remember correctly, that is like Microsoft Azure and IBM So that is providing like SGX service. But we tried that, but we just quit that because it costs a little bit, and we can get the same result when we do like our own local machine things. So we just stopped that, and we didn't do that, unfortunately.
Interesting. Well, if we can still see if there is adoption in production, that'll be interesting to see. Yeah, it's definitely useful and very, very interesting problem. Yeah.
Thank you.
Let's see. Are there other questions for Kim Tae?
Can I see the question list or like a Q&A list?
Yeah, sure.
There's
You should be able to see
question.
it on Vovo. I don't see any questions on Vovo. And I don't see any on
there's no question there.
So
people are not interested in our.
No, it's not that. It's not that. I don't know how this works, but it's persistent. But so you may, I don't know, you may receive questions after people watch your more detailed video. That's definitely possible.
Sure. I can answer the question later. Yeah.
All right. So if there are no other questions, perhaps we can move to the next speaker. So thank you, King Tae. So
thanks so much.
Yeah. So let me quit this slideshow. Our next speaker, okay, so our next speaker is Dan Crankshaw. Dan is a member of the systems group at Microsoft Research. He works at the intersection of ML and systems, investigating ways to use machine learning to improve cloud resource management, efficiency, and scalability as part of the Resource Central project. Prior to joining MSR, Dan completed his PhD at UC Berkeley, advised by Joey Gonzalez, where he focused on designing systems for low latency and efficient ML inference. And Dan is going to be talking about his paper on InfraLine, latency-aware provisioning and scaling for prediction serving pipelines. Once again, as a reminder to everybody, please use Vovo if possible for your questions, although I know we can use both Vovo and Zoom. We prefer that you ask your questions on Vovo. Dan, all yours.
Thank you.
Oh, sorry, let me share.
Yeah,
sorry.
That's okay.
Are you able to see my screen?
Yeah, great. Cool, it's just a couple PDF slides. So thank you for the introduction. So this is going to be a talk on some work I did at Berkeley as part of my PhD. And yeah, so I'm going to be talking about InfraLine, which is a system for serving prediction pipelines. You can go to the first content slide. So at a high level, the problem that we're trying to solve here is how do you efficiently serve ML prediction pipelines? And why do we care about prediction pipelines? Well, prior to starting this work on InfraLine, we'd been working for a few years on model serving systems and focused as many of these, the ML inference systems work is, on sort of serving a single model at a time, focused on things like efficient inference and ease of deployment and things like that. But when we started talking to industry practitioners, we kept hearing over and over again that people have more than one model that they want to deploy, and actually that they really have these prediction pipelines because they're building things like web applications and they get a request and they need to do a series of inferences on that request. Often these models are linked in some sort of control flow or data flow pipeline or DAG, and they need to make it all the way through this pipeline before they can return a response to the user. So what they really care about here is end-to-end latency of the whole pipeline. Now, this already introduces new challenges because when you think about trying to configure these pipelines, you have to configure each model separately because different models can have vastly different performance and resource requirements. But you have to do this configuration jointly because every model in the pipeline can contribute to end-to-end latencies. So that's one reason why this becomes complex, is suddenly your configuration problem is combinatorially large. The other reason that this is complex is that basically these prediction pipelines are basically queuing systems. And we really wanted to focus on real world applications and real world workloads. And in that case, what we observe in practice is that real workloads are bursty and stochastic. And so when you have this queuing system that you're trying to serve, you really have to worry about queue buildups. And so dealing with queuing effects and managing that correctly in the face of unpredictable and bursty workloads, and managing this combinatorially complex configuration space, sort of the twin problems that Infoline is tackling. So you can go on to the next slide now. So the way that we tackle this is with a hybrid architecture. The first piece of Infoline is this low frequency planner. The input to this planner is the pipeline itself, so each of the individual models, the latency SLO that the user wants to achieve, as well as a sample trace that we use for planning. And what the planner produces, it does some profiling of the individual models and then runs an optimization algorithm. And what it produces is, within a few seconds or tens of seconds, a physical pipeline configuration. When I say a pipeline configuration, what I mean is Infoline chooses the batch size, the compute hardware, and the number of replicas for each model in the pipeline, as we see in the slide here on the left. And the output of this planning is a physical pipeline configuration that is guaranteed to meet the latency SLO on the sample trace. But of course, reality is not necessarily reflected in the sample trace. And so while this provides a good initial configuration, it doesn't provide any guarantees about the running system. So that's what we use the high frequency tuner for. The tuner is essentially an autoscaler that runs continuously in the live serving system. And basically the way it works is we draw on this idea of traffic envelopes, which is a primitive in network calculus. And the basic idea with a traffic envelope is that it's a succinct and easy to compute characterization of a workload that captures the dynamics of the workload across many timescales. So the nice thing here is that these traffic envelopes will capture the burstiness of the workload, which can lead to things like transient queue buildups and kill our tail latency, even if we're even if we don't have diverging queues. But it also measures things like the overall request rate changing and just needing to scale up the pipeline. So the way we use traffic envelopes is, first we construct this traffic envelope for the sample trace used for planning. And this basically acts as an upper bound on the workload that the initial configuration produced by the planner is configured for. And then we can really easily maintain a traffic envelope for the online live query trace that we observe in the running system. And we just continuously compare these two. And if we detect that the online traffic envelope exceeds the sample, we know that we might be under provisioned. And so this triggers a rescaling event where we rescale each node in the pipeline, each model in the pipeline, to be provisioned for this new higher workload. There's of course a lot of details here that we have to address, and all of that's covered in the paper and my full-length talk. But that's the high-level idea, and I'd be happy to take any questions now.
Thank you so much, Dan. I'm going to stop sharing. I believe there's at least one question on what was, let me hit it.
Yeah, there's one that was asked a few days ago. Do you want me to go ahead and answer that one first?
So yeah, sure. As long as you can read the question from Carlos, yeah. It's good.
So this question is, can you comment more on how to determine the slack factor? Can you determine a good value for that automatically based on prior load history? So I didn't talk about it in my lightning talk, but when you dig into the details of how we rescale the models in the pipeline in this high frequency tuning component, we introduced this slack factor. At a high level idea, the way that we figure out the new number of replicas that we need for a model is we were able to, one of the nice things about this traffic envelope, which I won't go into the details of here, is that when we detect that the live traffic envelope exceeds the sample, the way that the traffic envelopes are constructed, that actually also tells us the new throughput, the new request rate that we need to reprovision for. And so in order to determine the the new number of replicas for a model. We take that new request rate. In the offline planning part, we've profiled all of the models. So we actually have a measure of the maximum throughput that each model can provide in its current configuration. And so naively, you would think that you would divide the new request rate by the throughput. That gives you a number of replicas, and take the ceiling, and and you're good to go. The problem here is that this doesn't account for queuing effects. And so the way that this slack factor works is it's basically a characterization of how much each model is essentially over provisioned by the planner. This over provisioning happens in order to absorb transient queue buildups without missing the latency SLO. So that's what the slack factor is. And the second question, can you determine a good value for that automatically based on prior load history? That is basically how we compute these slack factors. They're computed directly from the plan that is produced by the offline planner. And because that plan is planned on a sample trace, which is basically prior workload history, it sort of automatically takes that into account. And every time we rerun the planner, every hour, whatever the chosen provisioning plan is, we'll recompute those slack factors. It's a little bit of a heuristic. It's not a fundamental property of the pipeline itself or of the model itself. And so, if your workload varies dramatically between planning runs, that slack factor might change. But it's a pretty useful heuristic that avoids us massively over provisioning, but ensures that we don't miss the latency SLO, and that we're at least as over provisioned as the offline plan. And because the high frequency tuner is intended to react very quickly in order to respond to very quick changes in the workload, we're not so worried about being super optimal in the autoscaler itself. That's what the planner is for. I hope that answers their question, and they can always follow up with me offline.
So there is actually another question from Rodrigo. If you want, I don't know if you're able to read it. If you can read it. Otherwise, I can read it.
I'm seeing one in Zoom. There's another one in.
There's one.
Oh yeah.
So,
okay.
yeah.
Now I see the one. Okay. Yes. So Rodrigo asks, you mentioned earlier that this is not restricted to inference. Can you talk about other pipelines for which this is or isn't going to work? So that's a great question. This problem probably looks familiar to anyone who's worked on streaming systems or serving systems. The problem itself is a very general problem. Optimal configuration, meeting tail latency SLOs, these are very general problems. The reason that we restrict ourselves to inference in this paper and in this system is that with inference itself, we can make a bunch of assumptions about the pipeline and the nature of the nodes in the pipeline that don't hold for general computation. So I think the two most important ones are that these models, they're doing inference, so they're stateless. Of course, the model parameters are state, but it's static, it's not changing. And so that means that we don't have to stop the world to scale up a node. We can just add more workers, and as soon as they're ready, start sending traffic to them. That's one really critical piece, because that means that we can scale up much faster and so be much more aggressive in avoiding over provisioning. The other piece here is that pretty much the whole paper rests on profiling the models. When I say profiling, what we do is for a fixed model configuration, so a fixed batch size, type of compute hardware, GPU, ASIC, CPU, we observe that basically the variance in inference time is extremely low, which means that we can actually get very accurate profiles for the inference time. So ignoring queuing time or any of these other things, but for just the inference time itself, we can get really accurate profiles, which means that we can pretty aggressively provision the pipeline based on these profiles and be sure that we're not going to miss our latency SLAs. And so I think the interesting future direction here is sort of, in the serverless space, are there other types of computation, other classes of computation that have, at least similar properties that are profilable in some way? I don't work in serverless, I know a bit about it. Inferline is essentially a function serving system, although restricted to just inference. But I have to imagine that there's some interesting directions to explore there, and maybe even some primitives that you could ask, implementers of these functions to provide or to follow that would enable this. But I haven't really explored that direction much. So I think that there's definitely some more space there, and I think we're certainly going to need more work in, if we want to be using serverless solutions, serverless platforms for this type of low latency serving, whether they're machine learning models or not, we're going to need to explore solutions like this. But yeah, I think those are the statelessness and the ability to profile are the two restrictions in computation that Inferline rests on.
So that's interesting. Dan, so just as a time check, we still have a couple of minutes. So perhaps you can briefly answer Leju's question on Zoom. You can read out the question. And then
so they ask, how often do you have to build up or destroy any workflow DAGs, if at all? Does the DAG stay alive after it is built and running despite the actual workload you're receiving? I'm not sure I fully understand this question, and feel free to comment if I'm not answering the question you're asking. But I think one thing that might be useful to clarify here is that because we're able to profile these models very accurately, so digging into the planner a little bit more, at a high level, the planner itself, so just the offline planning piece, has three components. First, we profile all of the models, which I talked about briefly in the answer to the previous question. And then the second piece there is that we, using these model profiles and the sample trace, we built a pretty straightforward discrete event simulator that's able to really accurately estimate tail latency of the pipeline under different configurations. And the advantage of this latency estimator, this simulator, is that because of that, during planning, we never actually have to run the workflow DAG, the pipeline end to end. This is a big difference between prior work in streaming systems that use things like Bayesian optimization, stuff like that to do this. Because their nodes are more complex, they're often doing stateful computation. They're not able to profile them, which means that in order to estimate whether a given configuration leads to improvement in performance or meets a latency SLA, you have to actually run the streaming system or the pipeline in that configuration. So during planning, we never have to build up the workflow DAGs. And then does the DAG stay alive after it is built? So once planning is done, we do, we're now serving the workflow DAG as a live service. So it stays up the whole time there. Yeah, I hope that answers the question.
So just to add to what I was asking, because you were saying, because what I was trying to ask was how, like, by staying alive, I mean, do you have a process that keeps all this? I guess it doesn't keep any updating states, but I guess you have to have a memory space that hold all the models and everything. So like, does that, because I think you mentioned once that it's based on functions. So basically, this is your pipeline is just a series of functions. So I guess that answers my question somehow. So like, I'm just curious, do you have to, let's say if you don't receive any events in the near future, do you destroy your pipeline and establish somewhere else? In that case, you'll have to ship your states and everything.
Yeah, that's a great question.
So just once again, sorry, Dan.
Yeah.
It is a great question, but on time check, it is 8:30. So how do we do this? Maybe you can take 30 seconds and then
Yeah,
you
I can.
continue it on Wova, perhaps?
Absolutely. The really brief answer is that we run each of these models in Docker containers. We assume that there's a continuous workload. The autoscaler does have a scaled down component, but we keep at least one replica of every model alive so that we can service a single request without having to build up a new replica.
Thank you.
Thank you. Thank you so much,
Thank
Dan,
you.
and thank you so much, everybody, for the questions. Keep them coming. Let's move forward for the next talk, which is by Aditya Dhakal. Aditya is a final year PhD candidate at University of California, Riverside. He's interested in edge clouds, use of GPU for ML and network function virtualization, and he will be in the job market soon. And he's going to be talking about GSlice, controlled spatial sharing of GPUs for a scalable inference platform. So let me share GSlice.
Thank you, Sri.
If I can.
Okay, thank you. Looks great. So it's our work, GSlice, which we did in UC Riverside with a colleague and my advisor, KK Ramakrishnan. Can we go to the next slide, please? Okay, so basically the motivation is we used some DNNs, we did some experiments, and we saw that if you keep increasing the GPU percentage, you will see the latency of inference decreases, but up to a point. After a point, it starts like very minimal decrease or no decrease at all. So some of these DNNs are unable to utilize the GPU fully. So like there is some spare GPU capacity that we could use. And the good idea we can do is multiplex the applications together so that the GPU will be utilized properly. But like multiplexing GPU is, there are many different ways to do that. The default way would be two applications. If you run together, they will temporarily share the GPU. So application gets a time slice and another gets a time slice and so on. That would not help with utilization as much. There is also spatial sharing of GPU that is done by using CUDA multiprocess service or MPS. It has two flavors. It allows multiple kernels to run on GPU concurrently. The uncontrolled or the default one, there you can run applications, but the GPU determines which kernel or which application gets how much resources. The GPU subsystem determines that. And a controlled one, where a user can fix how many percentage of GPU do you want to give to a certain application. If you see at the second and third plot in the middle, if you have uncontrolled spatial sharing, if you introduced a third, as I did in this experiment, in 3 seconds, I introduced a third DNN. You see there is a latency spike on the first one, it doubles. So then the GPU subsystem is determining that the one application gets more resource than others, so that is affected. But if you have a controlled spatial sharing in the next plot, and you pick out the right percentages, like right means like whatever appropriate percentages you think, and then you run them and you see that you can provide a compute isolation. The latency doesn't increase when you introduce a new DNN. Also, you can see that the red one, DenseNet, is still getting around 20 millisecond latency, even with 25% GPU. So probably it doesn't need more GPU than that. But there are also challenges of using this control spatial sharing, especially with the CUDA MPS. Once you give a certain amount of resource, like you say this DNN gets 50%, then that resource is fixed. It cannot be changed when that application is still running or the process is still alive. What we can do is we can just we can just end the process and start a new one with different percentage. But these DNNs and their platforms, they take like few seconds to get ready. Like it can take seconds, even tens of seconds to get ready if the DNN model is quite big. So our solution, GSlice, what we do is we made the inference platform. with dynamic resource allocation, and we avoid this huge downtime. Can we go to, yes, thank you. So I have noted some of these features, what we do. We provide control spatial setting of GPU with fixed percentages, as I have explained. And how we do this dynamic readjustment is we keep an active and standby pair alive. So active is inferring. It is working with the GPU as well as getting the request from the user, while the standby is basically sleeping a process. When it is a time to change GPU percent, let's say the active is 25%, we want to go to 50, what we do is the standby will initialize, do the GPU initialization with 50%, and then start loading the model into the GPU, while the active will continue serving the requests that are coming. So when the standby is ready, then we switch from active to standby. So we have basically masks the time it takes to load a model into the GPU. As it is an inference serving platform, we also have other features that are like adaptive batching, so that we can serve any request within latency SLO. And we also have GPU resident DMA that can scatter gather the data if we are getting something from raw packets or packets in DPDK settings. And there is also parameter sharing, where if a model is already loaded in an active process, then you don't have to copy the parameters again, because you're just creating in the replica of model. So you can use that already loaded parameters in GPU to create the new replica. And we can see G-Slice does better in throughput, better than just batching alone. And where G-Slice gets good is in a multiplexing scenario, as shown in the last figure, where there are multiple applications running together. You can see like the S, that is, the S means for us, it is self-learning adaptive batching. The batching only would not give a high throughput, because the MPS can give resources to an application without thinking. So it is not really balanced. Some applications get more resource, and they will take away resources from other applications. So the throughput of other applications are also affected. So basically there's an interference from a big compute heavy application. While in G-Slice, since you can fix partition like GPU as you desire, you can keep high throughput for even other applications without being affected by some heavy application running there. So overall, like G-Slice improves in inference throughput. We also mask the time to change the GPU percentage, and we do it dynamically, and we reduce the downtime from seconds to 100 microseconds. And all other features are more explained in my long talk. Please do see that. Thank you. I can take the questions now.
All right. So thank you so much, Aditya. There are a few questions, in fact.
Yes.
Let's go to. Let me go to. There's a question from Preeti Murthy. How does G-Slice perform on a model as more GPU resources are given? This is in the context of the first few slides, which show how beyond a knee point, latency of a mode does not decrease.
Yes. So what we have seen is like where the knee point is dependent on how big the batch size you are inferring, as well as what the model is. Usually DNN models have a lot of variety. Like some are designed to be very, very quick, and they're very lightweight, like AlexNet or MobileNet, if we talk about new one. And some are compute heavy. The compute heavies tend to require a little bit more GPU before the latency flattening out, while the light ones are like, usually if you even give you 10% GPU, they will not improve the latency anymore. So it really depends on like what DNN you are using. Some DNNs can utilize GPU quite a bit. And also if you increase the batch size, you also would give more GPU to be able to do that, to be able to, to be able to infer while respecting the SLO.
So we have a couple of other questions also on Zoom. So this one is from Ubaidullah Hafiz, who asks, assigning a fraction of GPU to a model refers to a fraction of GPU memory or fraction of total number of GPU cores?
Okay, so that is a good question. GPU are, they have multiple SMs. If you say B100, B100 has 80 streaming multiprocessor. So what MPS currently does is, like, if you give an integer value of GPU percentage, it will give you the closest approximation of how many SMs you get. So you get the SMs in pairs. So if you give 50% GPU, you're getting 40 SMs for that application. If you give 25% GPU, you are getting 20 SMs for that application in V100 GPU.
All right, so there is one more question, two more questions, in fact, both from Simon. First one is, to improve utilization, why not just increase batch size?
Yes, batch size will increase the utilization. But first point is, while you are doing inference, you are bound by a certain latency, a certain SLO. So you cannot have a very large batch size. If you are bound by 25 millisecond, 100 millisecond, you will have a point where you cannot exceed. And even increasing the batch size, yes, it will increase utilization, but up to a point, you will still see that latency curve being flattening out after certain GPU percentage, because there are a lot of things in DNN, how it is implemented in CUDNN while running in GPU, that there are parallelizable kernels, but there are also time between the kernels where there are sequential tasks. So you can parallelize as much as possible, but those sequential tasks still exist. So you will still see that latency being flattened at some point. There are some DNN where you can really keep improving as you go towards 100%. Especially I saw that with VGG19, that it was a very heavy computation. So if you have a big enough batch size in VGG19, you can pretty much see the latency being lower till 100%. But some other DNN, they will pretty much have a knee point at somewhere.
Right, so there are a couple of other questions, one more from Simon and one more from Baolin Lee. So perhaps we can take the Baolin Lee's question first, since you answered one of Simon's questions. Just as a time check, I think we have 3 minutes left, so maybe you can make your answer pretty brief, a minute, okay, and that would help. So question is, when you share GPU with multiple DNNs, do you have trouble with GPU memory not large enough to host all models?
Yes, that can happen if you have a very, very large models, especially like, let's say if a model takes half of the GPU, then you want to change and you want to start a replica. So the replica will, the saddle or standby will also take half of the GPU memory. So that is still our limitations. We try to minimize it by having this parameter sharing. But yes, there will be a point where you can only have like X number of models in GPU because you will run out of GPU memory.
Good. So the other question from Simon is, by sharing the GPU, multiple tasks will also load data from main memory to GPU simultaneously. Won't they affect each other's performance?
Yes. Yes, for acknowledging the question, we have not seen them affecting each other's performance while we were doing our experiment. The latency and the throughput were not affected. And this is actually a follow-on work. We are trying to determine that how much more we can do with GPU in terms of this memory, so that we can reach a point where they actually affect each other. In the experiment where we did with G-Slice, up to 4 or 5 DNN running together and concurrently inferring the request with batch size of 8 or 10, we did not see any kind of performance impact related to the memory.
Excellent. So thank you so much, Aditya. I think you managed to answer all the questions also in time, so that's fantastic.
Thank you.
All right, so let's go to the last speaker of this session, who is Yangrui Shen. Yangrui is currently a full-time PhD student of the Department of Computer Science in the University of Hong Kong. His supervisor is Professor Xuan Wu. His research area is distributed machine learning system. And Yangrui is going to be talking about elastic parameter server load distribution in deep learning clusters. So all yours, Yangri. So before this talk begins, just a reminder, please keep the questions coming. You can definitely ask a question on both platforms, Zoom and Wova. We definitely prefer that you ask the questions on Wova because it can be persisted there. All yours. Yeah, right, Yangri. Oh, I need to share. Good. Sorry,
Okay.
almost forgot.
Okay, thanks for the introduction. Hello, everyone. I'm Yang Chen, and now I'm going to talk about the main idea of our work. So in this work, we propose PSLD. It's a dynamic PS load distribution scheme, which focuses on mitigating PS regular issues and accelerating DM training. Our motivations mainly root in the following aspect. So in the first place, we observe that the imbalance and in current machine learning frameworks, the parameter assignment is imbalanced and static, which means that the workload or the parameters over different parameter servers are different. And this assignment strategy is fixed, which remains unchanged after the training starts. And this imbalance and static parameter assignment will result in performance degradation, decreasing the training speed of the training job. And also we found that the performance of each PS is different during runtime, and some PS may even become stragglers due to resource contention and interference in a shared cluster. We found that this straggler issue can be solved by reassigning the parameters across PS. For example, if we observe a straggler during runtime, we can move its parameters to other good PS to reduce its negative impact on the training job, to reduce to mitigate such PS straggler issue. And based on these motivations, we propose elastic parameter server load distribution scheme, which we dynamically reassigns the parameters across PS. With the epsilon greedy policy, the figure right-hand side shows the workflow of our work, of our system, and we will profile the performance during runtime of each PS. And if we detect a straggler, we will start the parameter reassignment process, and we will exploit the superior PS that we identified previously for the majority of the parameters. And at the same time, we will also explore OPS for some parameters. And this exploration is also important to avoid getting stuck into a local optimum, because the profiled performance may not be 100% accurate. And would you please go to the next slide? Thanks. And so here's the implementation. And we implement our system based on two popular parameter server architectures. The first one is vanilla MaxNet PS architecture, and also targeting the generality. We also implement our system based on the BiPS. It's widely used in ByteDance training clusters, which can interact with multiple machine learning frameworks. And the figure right-hand side shows the procedure of adding one PS into a job. When we detect a large scale parameter servers regular issues, which means that the current good PS are not enough to handle all the parameters. So we will start the dynamic PS scaling to add new PS into the job to share the parameters. And we evaluate our system on both controlled PS straggler patterns and real-world straggler patterns. And the results show that we can achieve up to 286% improvement over baseline across different DM models and different straggler patterns. And that's pretty much about the main idea of our work. If you have any question, I will be happy to answer. Thanks.
Thank you so much, Angry. So let me head over to the questions.
I see a question in the Zoom.
Oh, yes. This is a question from Simon, who asks, how large is the overhead of the reassignment itself? Is it very small, or you somehow manage / hide it?
Yes, this is a great question. And as you have mentioned, we implement our system on two PS architectures. So the first one is the by PS. This parameter server architecture is only for the parameter aggregation only. So which means that the PS do not store the global model of the training job, and we only need to modify the mapping, the parameter to server mapping on the worker side. So in this case, we do not have much overhead when we reassign when we do the reassignment. And also we implement our system based on the vanilla MaxNet PS. And in this case, we do need to migrate the parameters across PS. And this is negligible because we overlap the parameter movement with the parameter pool, the gradient, the parameter pool response. So this will hide some part of the overhead. So overall, the overhead may be less than 1 second, and I think it is negligible, acceptable.
All right, so I don't see any other questions. I had one quick question myself, which is this available as part of TensorFlow or any other learning framework, distributed learning framework?
Actually, we haven't merged this work to the current open source machine learning work, but machine learning training framework. But we did base our work on the current popular machine learning frameworks. So for the implementation on the vanilla MaxNet PS, this is based on the MaxNet framework. And for ByPS, we target the generality because ByPS use the Horovos API to interact with multiple training frameworks. So in other words, we can run our system on multiple training machine learning frameworks such as PyTorch, TensorFlow, MaxNet on the ByPS implementation.
And this follow-up question, since I don't see any others, was your Strawman comparison in your paper? I need to check, but can you briefly tell me what the Strawman comparison that you showed in your charts were?
Sorry, I don't quite get your question.
In your plots, there was a Strawman comparison with PSLD.
Okay.
So I was curious what that Strawman was.
Yes, this Strawman method is pretty much the naive reassignment implementation because we will profile the performance of each PS during runtime, and it also will detect the straggler issue. And when doing the reassignment, it will reassign the parameters proportionally according to the profiled performance, which means that if we detect the ratio of the performance for the good PS and bad PS is 10:1, and then we will about assign most of the parameters to the good PS and less parameters to the bad PS. But this is not very useful in the runtime when we do the experiment because it cannot handle the straggler, the transient stragglers, because it cannot sense the straggler resumption, which means that when the straggler becomes good again, they cannot do some reaction. They cannot detect this resumption.
Interesting. I don't see any other questions. Perhaps we may get more questions from your full talk. All right, so if there are, first of all, thank you, Henry, for the talk. So if there are no other questions, I think that brings the session to a conclusion. Okay. Rodrigo and Christina, so you got 6 minutes back.
Great, thank you, Sri, and thank you to all the presenters. So that is the end of the official program for SoCC 2020. The Gather platform will be open for a little bit longer if you want to head over there and ask any follow-up questions to the presenters. Otherwise, thank you all for sticking until the last session. We hope you enjoyed the program we put together, and then special thanks to all the presenters, the authors, keynote speakers, panelists, and the organizing committee, including the session chairs. And hopefully next year we can have the conference in person. So Benching or Rodrigo, anything else to add?
No, you spoke beautifully. Thank you. I echo everything that Christina said, and I would just like to thank everybody again. This was a big experiment. We were learning as we're going. And the last thing I would like to ask is that you go and fill the survey so that we can learn from this as much as we can. But thank you again. And hopefully see you guys next year in person.
Bye.
All right.